torus of revolution. Okay, forget. So how is the torus got? How? You take a circle in this and then rotate about the z-axis. So you have two numbers involved. One is this distance, there is distance there, and of course the radius is involved. Okay. So the usual way parametric representation is given is like this: a plus b cos u cos v, a plus b cos u sin v, and then b sin u. Here a is greater than b, greater than 0. So b, so if b is the radius of the circle that you take and a is the distance here. So this example is something that will show. All the earlier examples, the curvature was a constant. At all points it is 1, or all points it is 0, and so on. So this is an example where curvature is a function of the point, not a constant, varies with point to point. So let us calculate. Okay, phi u a minus b sin u cos v, a minus b sin u sin v, b cos u. So this is what you will get. Various values of E, F, G, L, M, N. So the curvature is therefore given by this. Depends only on V though. So this is going to be denominator is always positive because A is greater than B. So A plus B cos U is always positive. So the sign of the curvature therefore depends on the sign of cosine U in the numerator. So wherever U is cos U is positive, the curvature is positive. Wherever it is 0, the curvature is 0. And wherever it is negative, curvature is negative. So I have marked the different parts of the torus where these three possibilities occur. So positive curvature, so to say, on the outside, for all points outside on the outer surface of the torus. So there is a top circle, of course there is a bottom circle also. So if you keep your this playing ring, whatever it is called, right, on a flat surface, it will the points of contact of the ring and the plane will be a circle. So that is, so you have two circles of that type, one on top, one at the bottom. So at all points on that circle, the top circle and the bottom circle, the curvature is 0. Inside, point inside, the curvature is negative. So around that hole there, right, the curvature is 0. So we also had a picture earlier marking this, but I have drawn that anyway. So on the torus, therefore, you have points with all possible signs for the curvature, positive, negative, or 0, on the same surface. Okay. We look at surfaces of revolution in general. Okay. So you take a curve, say in the YZ plane, and rotate the curve about the Z axis. So to write down the parametrized form of the surface, you have to know the parametric equation of the curve that you rotate. Okay. So if your curve is given by Fu and Gu, alpha u is equal to Fu comma Gu, is a curve that you rotate about the z-axis. The curve is usually referred to as the profile curve. So because if you take the surface and take the what are called the profiles on the surface, so you will get the curve. So in any case, so once you have the parametric equation of the profile curve that you rotate, then the parametric equation of the surface can be written in this form. You are going to rotate, so naturally you get cosine and sine. So each point is going to give you a circle, right? Whenever you have a curve, so and rotate about this, so each point here is going to describe a circle with center on the z-axis. So you will get the parametric equation of the surface in this form: Fu cos V, Fu sin V, Gu. Of course, the cylinder is also of this type, okay, where your profile curve is a circle. The torus cylinder, how do you get a cylinder? Rotate a line, right? Like that. Vertical line, rotate like that. So all these are examples of surface revolution. But for a general surface of revolution, you can use the earlier formula and get a formula in terms of the functions which give you the profile curve. The formula reads like this. Fu and Gu are the functions defining the curve like that. So G prime, F prime G double prime minus F double prime G prime over F times F dash square plus G dash square whole square. So you can calculate the curvature using this formula even for the torus or for the cylinder, right? But of course, using the earlier formula directly is fine enough. So let us look at a particular example of this kind, which gives you constant negative curvature. We already have seen examples of surfaces with constant curvature 0. What are the examples? Plane, cylinder also, right? Although of course the difference between the plane and the cylinder is that the plane, the curvature is 0, but what about the eigenvalues? Both are 0, right? Both eigenvalues are 0, and therefore the product is also 0. But in the case of the cylinder, what happens is one eigenvalue is 1, the other eigenvalue is 0, but the product is still 0. Okay? So the Gaussian curvature is 0 in both cases, but the principal curvatures and the mean curvature differ. They are not the same. So these are examples of surfaces with constant curvature 0. And then you have a sphere, which is an example of positive constant curvature. Everywhere the curvature is 1. If you take the unit sphere, or in general 1 over the radius of the sphere. So just to complete the picture, we'll look at an example of a surface whose curvature is constant negative. So in this case, so this is what is called the pseudo-sphere. Yes. So think of this on lying this way and rotate like that. So you will get this. This tractrix itself can be parameterized in different ways. Of course, any given curve has different parameterizations, can have different parameterizations. So one parameterization is this, which we will look at. So tractrix alpha u is equal to cos u plus log tan u by 2. Okay, this is a profile curve. So pseudo-sphere is the surface of revolution. With profile curve with the tractrix calculate the curvature of the pseudosphere using this formula now. So what is, so Fu now is sine u, g of u is cos u plus log tan u by 2. So the parametric representation for the pseudosphere is given by this, where Fu and Gu are given like this. So you calculate the derivatives of these two functions and see what this is. F dash u is cos u, F double dash u is minus sine u, so we need the first and the second derivatives of both the functions f and g. That's all. I mean, it should not be too much complicated calculations. So log tan you have to differentiate. So 1 over tan, and then when you differentiate tan, you get secant square. And then there is a half. Okay? So find one more derivative. Cot, because this simplify cot and the secant. So this is cos by sine, right? One cos will go off with this secant. So what do you get? So this is secant u by 2 divided by sine u by 2, right? So cosecant. So secant and cosecant. So you have to differentiate this now. Differentiate secant, you get secant tan, is it? And for cosecant, you will get a negative sign. So maybe we will write it here. There's not much space there. We'll get another half, I suppose. So the 2 will, so 2 will go with that, right? 1 over sine 2u. Oh, minus again, right? When you differentiate cosecant, so minus so now just plug in all the values there. F dash square plus g dash square, do you get something simple? one here. So we can do all the simplifications and then plug in, right? So what is f dash square plus g dash square? F dash square is cos square cosecant u minus sin u whole square. Is that right? Okay, so 1 minus 2 sin u cosecant u plus sin u cosecant u is gone, right? So minus 1 plus cosecant square u. Is this cot square or minus cot square? This one f dash g double dash dash is cos u minus cos u plus minus f double dash sin u onto g double dash. Oh, there is a minus anyway, so no, this is what? F double dash into f dash, g dash, right? So minus sin u plus cosecant u. The sign is okay, or so minus cos square minus sin square, that will give you minus 1 cosecant cos cosecant cot. What does that give you? Cot square, is it? Cos into cosecant is cot, right? So this is another cot. So cot square minus cot square. This is already taken care of. What about this? So minus plus cot again. Oh, not this here. Okay. Sin u into cosecant u. So there is 1 with plus sign. So that gives you only minus cot square. So what is k now? G prime so everything okay so far? So k is equal to so this is minus cot square here. This is okay? I have copied correctly. So k is g prime minus sine u plus cosecant u to this one minus cot square. Okay, f is sine u. This is cot u. Cot square, huh? Okay, that's what I was. Here is cot is fine. Oh, square of that, whole square. Okay. This is okay? Whole square is fine. Otherwise it is okay. So sine square. Oh, only this one. Okay. Square of the, so cot square here. So this is this. This is cot square. Square of that. You get minus 1. The surface which has constant curvature equal to minus 1. Constant negative curvature. So this is model, so to say, for the hyperbolic plane in contrast to the Euclidean plane. So what is a plane anyway? So it's a two-dimensional surface, right? The Euclidean plane is a two-dimensional surface of constant curvature 0, right? The surface of the unit sphere is a two-dimensional surface of constant curvature 1. You have two other which are more frequently used in most contexts than the pseudo-sphere, because they are parts of the Euclidean plane itself, but given different metrics. So pseudo-sphere is a hyperbolic plane, or if you want. So this just means that the two-dimensional surface equipped with the Riemannian metric that we are going to talk about in the afternoon. So two other important and most commonly used models are the upper half plane model and the unit disk model. So the upper half plane, open upper half plane, y greater than 0, or imaginary part of z greater than 0, if you think of it as a complex plane. And this is the open unit disk. This is usually called the Poincare upper half plane. Probably the metric in the unit disk case was also many times referred to as the Poincare metric. Probably it was due to Beltrami. So we'll say something more about this in the afternoon. The upper half plane equipped with a certain Riemannian metric, right? It's called the Poincare metric. Upper half plane H, okay? H with the hyperbolic metric or the Poincare metric. Here it is the open unit disk D with the hyperbolic metric. So all the three things are equivalent. That means we can have a diffeomorphism between the two, which preserves the metric, which preserves the inner products. Okay. So these are essentially the same space as manifolds, as Riemannian manifolds. They are isometric. So even global isometry. Okay. So you know, for example, between the upper half plane and the unit disk, you know how to go from one to the other. Right? You will have seen that the Mobius transformations, right? Z minus I by Z plus I transforms the upper half plane to the unit disk, open unit disk, and the real axis to the circle, the unit circle, right? So that essentially is going to give you an isometry between the two, with the metric, the Poincare metric here and the hyperbolic metric there. That's a diffeomorphism which also preserves the metric. So it's an isometry that way. So everything is going to be preserved. Okay, so curvature is going to be preserved. So the basic theorem before we pass on to Riemannian metrics is the fundamental theorem of Gauss. This basically says the Gaussian curvature on a two-dimensional surface is intrinsic. That is, it is an invariant under local isometries.